something ancient was coming home. 4.5 billion years ago, when our solar system was nothing more than a spinning disk of dust and gas around an infant star, a chunk of rock and ice was violently flung outward into the eternal darkness. It tumbled through the void alone and frozen, passing through alien star systems we will never know. And then, in the summer of 2024, astronomers spotted something unusual. A faint blur moving through the constellation of Ursa Major. They named it 3I Atlas, the third confirmed interstellar visitor to pass through our solar system. But unlike its predecessors, the mysterious Oumuamua and the well-behaved comet Borisov, this object would soon reveal behavior so strange, so unprecedented, that it would challenge everything scientists thought they understood about comets. The object was moving at 58 kilometers per second relative to the Sun, far too fast to be captured by our star's gravity. Its trajectory showed an eccentricity around 6, meaning it was on an extremely hyperbolic path, destined to pass through our solar system only once before returning to the interstellar void forever. The timing of its arrival could not have been more dramatic. 3I Atlas had chosen to visit during one of the most violent periods our Sun experiences. Solar maximum. Every 11 years, our star undergoes a complete transformation. Its magnetic poles flip, twisting and churning the plasma that boils across its surface. Dark sunspots appear like bruises on the solar face, each one large enough to swallow Earth whole. From these magnetic wounds erupt solar flares, brilliant explosions of light and energy that can outshine entire galaxies for brief moments. But the most dangerous phenomenon of solar maximum is the coronal mass ejection. Imagine 1 billion tons of superheated plasma, magnetized and violent, hurled into space at speeds exceeding 1,000 kilometers per second. These eruptions tear through the solar system like cosmic tsunamis, carrying enough energy to strip away planetary atmospheres. When they strike Earth, they compress our magnetic field, triggering geomagnetic storms that paint the sky with auroras and threaten our technological civilization. The current solar cycle, known as Solar Cycle 25, had already exceeded all predictions. Forecasters expected a quiet maximum, similar to the week cycle before it. Instead, the Sun erupted with fury. Officials at NASA confirmed that the Sun had reached the peak of its 11-year cycle, a period of intense solar activity that could lead to more severe geomagnetic storms. In May 2024, a G5 superstorm struck Earth, the most powerful in 2 decades. Auroras danced across skies as far south as Texas and New Mexico, visible to millions who had never witnessed such beauty. Satellites tumbled out of orbit. GPS systems failed. Farmers lost millions as precision agriculture technology went dark, and through this chaos, 3I Atlas was accelerating inward, racing toward its closest approach with the Sun. Scientists tracking the object noticed something immediately wrong. If this was a comet, it was behaving like no comet ever observed. Comets are dirty snowballs, fragile remnants from the birth of planetary systems. As they approach the Sun, heat vaporizes their ices, creating the magnificent glowing tails that have terrified and inspired humanity for millennia. But 3I Atlas showed unusual behavior from the start. Throughout its inward journey, observations revealed a complex and evolving object. The Hubble Space Telescope took its first images on 21st July 2025, which revealed its coma in high detail and constrained its nucleus diameter to below 5.6 kilometers. The Vera C. Rubin Observatory had serendipitously imaged 3I Atlas during its science validation observations, showing a slight increase in the comet's coma diameter. These early observations painted a picture of an active but enigmatic visitor. Mission controllers at NASA scrambled to get a better look as the object passed through the inner solar system. Multiple different telescopes showed that the comet's coma had a reddish color indicative of dust, similar to that of the previous interstellar comet 2, I Borisov. But as scientists continued monitoring, they noticed something strange. A study published in August 2025 reported that 3I Atlas coma had become redder throughout July 2025, indicating an evolving surface or coma composition as a result of increasing cometary activity. Then came October 29, 2025. Perihelion, the moment of closest approach. 3I Atlas swept past the Sun at a distance of about 130 million miles, roughly 210 million kilometers, approximately 1.36 astronomical units from our star. This placed it closer than the orbit of Mars, plunging directly into the fury of solar maximum. The Sun was raging during this period. Solar activity remained at peak levels, with the potential for severe geomagnetic storms and increased solar flare activity. Any normal comet approaching perihelion during such violent solar conditions would face extreme challenges. The intense radiation, powerful solar wind, and energetic particle bombardment would test the structural integrity of even the most robust cometary nucleus. Scientists watching 3I Atlas expected fragmentation, rapid outgassing, or dramatic changes in brightness. What they observed instead would confound every prediction and force them to reconsider the nature of this mysterious visitor. As the comet approached perihelion while near superior conjunction from Earth, ground-based optical observations became extremely difficult at heliocentric distances less than 2 astronomical units. The comet approached its superior conjunction on October 21st at only 1.9 degrees solar elongation from Earth, creating a gap in observation just as the comet approached its maximum heating at perihelion. But space-based solar coronagraphs and heliospheric images maintained their vigil, continuing to track 3I Atlas through its closest approach to the Sun. What these instruments recorded during those critical hours would mark the beginning of one of the most perplexing mysteries in modern astronomy. The interstellar visitor was about to reveal its first surprise, a dramatic transformation that would signal the start of increasingly bizarre behavior. Scientists analyzing the data knew they were witnessing something unprecedented, something that would challenge fundamental assumptions about comets, interstellar objects, and perhaps even the limits of natural phenomena in our solar system. The transformation began on October 29th, and what the satellites witnessed defied every model, every prediction, every assumption about how comets should behave. Using the GOES and SOHO coronagraph satellites positioned to observe the Sun, scientists maintained their vigil on 3I Atlas during its perihelion passage. These space-based observatories had been specifically designed to study solar phenomena, tracking coronal mass ejections and solar flares that threatened Earth. But now they were trained on something far stranger, an interstellar visitor entering the most dangerous region of our solar system. The object became 400 times brighter within just a matter of days. To understand how shocking this is, consider that normal comets approaching the Sun typically brighten by a factor of 10 to 100 at most. Their ices sublimate, creating clouds of gas and dust that reflect sunlight. The process is predictable, well understood, documented in thousands of observations over centuries of astronomy. But 3I Atlas was not following the rules. Data from multiple observatories revealed that the comet's brightness increased dramatically, following an inverse relationship to its distance from the Sun raised to the power of -7.5 plus or minus 1. This rate of brightening was far higher than what is typically observed in comets within the solar system, suggesting a possible difference in composition or surface reaction to solar radiation. Scientists analysing the data struggled to find natural explanations. Something about this object's interaction with solar radiation was fundamentally different from anything they had seen before. Then came the colours. Throughout its approach to the inner solar system, 3I Atlas had displayed a reddish hue, entirely normal for a comet. The red colour comes from dust particles in the coma. Tiny grains of rock and organic compounds that scatter sunlight preferentially in the red wavelengths. Every comet humanity has ever studied shows this characteristic. Multiple different telescopes confirmed that the comet's coma had a reddish colour indicative of dust, similar to that of the previous interstellar Comet 2, I Borisov. But then, something changed. A study published in August 2025 reported that 3I Atlas coma had become redder throughout July 2025, indicating an evolving surface or coma composition as a result of increasing cometary activity. The reddening intensified as the comet approached perihelion, exactly as scientists expected. More dust was being released, more organic compounds were sublimating, more material was being stripped from the nucleus by solar heating. Everything seemed to be proceeding normally. And then the comet turned green. The shift happened suddenly, catching astronomers completely off guard. Where there should have been deepening red from increased dust production, instead the coma took on a distinctly green coloration. Green comets are not unheard of. The colour typically comes from diatomic carbon molecules, C2, that glow green when energized by ultraviolet radiation from the sun. Several comets suddenly shift to green raised questions. Scientists barely had time to process this anomaly before 3I Atlas did something even more inexplicable. During its closest approach to the Sun on October 29th, the comet changed colour again, this time from green to blue. The data from LASCO and CSER 1 instruments confirmed that 3I Atlas appeared bluer than the Sun itself, a characteristic completely inconsistent with known cometary behaviour. Typically, dust particles scatter sunlight, resulting in a redder hue. The observed blueness implied that emission from excited gases might be dominating the reflected light, a phenomenon rarely seen in such bodies. This was the opposite of what natural comets do. As comets approach the Sun, solar heating drives off volatile ices first, then deeper, more refractory materials. The colour progression should go from blue or green when volatile gases dominate, toward red as heavier dust production increases closer to perihelion. But 3I Atlas was doing exactly the reverse. It started red, shifted to green, and then turned blue at its closest approach, when it should have been at its reddest. Two possible natural explanations existed for this behaviour. First, the comet could be releasing an unknown bright blue gas. Something not seen in any previous cometary observation. Scientists catalogued dozens of molecular species in cometary comae: water vapour, carbon dioxide, methane, ammonia, cyanogen, and many others. Each produces characteristic emission lines when excited by solar ultraviolet radiation, but none of the known cometary gases could account for the intense blue coloration observed. The second possibility was that the comet was beginning to fragment, breaking apart under the intense thermal and tidal stresses of perihelion. When comets fragment, they often expose fresh material from their interiors, material that has never been processed by solar radiation. This fresh ice can produce unusual colours as it rapidly sublimates. Fragmentation events have been observed in many comets, and they often result in dramatic brightening and colour changes. But fragmentation was quickly ruled out. Observations after perihelion confirmed that 3I Atlas remained completely intact. Its nucleus had not broken apart. No secondary fragments were detected trailing behind the main body. The comet emerged from its solar encounter structurally sound, its core unbroken despite experiencing conditions that should have torn it apart. This meant that whatever was causing the blue coloration was not fragmentation, but something else entirely. That left a third explanation, one that some scientists were reluctant to even consider. The blue coloration might be coming from inside the object itself, not from surface sublimation, not from dust scattering, not from known molecular emissions, but from some internal process or mechanism that became active during perihelion. The timing was suggestive. The color change from green to blue happened precisely at closest approach, exactly when the object would experience maximum solar heating and radiation pressure. The CCOR1 instrument detected a diffuse glow extending up to 300,000 kilometers around the object, comparable to the carbon dioxide plume recorded by the SPHEREX Space Observatory between August 8th and 12th, 2025. This extensive halo indicated active outgassing or sublimation processes, possibly triggered as the object neared the Sun. But the scale and intensity of the activity far exceeded normal cometary behavior. Experts argued that, given its temperature is far lower than the Sun's 5,800 Kelvin, the blue coloration cannot be attributed to thermal radiation. Instead, it might indicate the presence of volatile compounds or energetic reactions on or near its surface, possibly driven by solar heating or unknown chemical processes. The reason for 3I Atlas's rapid brightening, which far exceeds the rate of most Oort cloud comets, remains unclear. The blue emission is very surprising, as dust is expected to redden scattered sunlight. This discovery marked the 9th recorded anomaly associated with 3I Atlas, joining a list that includes irregular spin, non-gravitational acceleration, and unexpected gas emissions. But the anomalies were not finished. What happened next would shake the astronomical community even more profoundly. As the blue glow faded and 3I Atlas emerged from behind the Sun, tracking stations detected something that should have been impossible. The object had changed course. As 3I Atlas emerged from behind the Sun in early November 2025, astronomers eagerly resumed their observations of the interstellar visitor. They expected to see a comet continuing on its predetermined path, perhaps slightly altered by the gravitational pull of the Sun, following the elegant mathematics of Newtonian mechanics that had predicted the motions of celestial bodies for over 3 centuries. What they discovered instead would force them to confront the most profound anomaly yet. The object had changed direction, not in the subtle, predictable way that comets normally deviate from purely gravitational trajectories, but in a dramatic, unexplainable manner that violated everything astronomers thought they understood about cometary physics. This marked the first detection of strong non-gravitational acceleration in 3I Atlas, and it was unlike anything previously recorded in cometary science. Non-gravitational acceleration, often abbreviated as NGA, is not entirely unknown in cometary studies. When comets approach the Sun, solar heating causes their ices to sublimate, releasing jets of gas that can act like tiny rocket engines, slightly altering the comet's trajectory. This effect has been observed in many comets, and astronomers routinely account for it when calculating orbital paths. The famous Halley's Comet exhibits non-gravitational acceleration. So does comet 67P Churyumov-Gerasimenko, which was studied in exquisite detail by the European Space Agency's Rosetta mission. But 3I Atlas was different in a way that defied explanation. Throughout its entire journey inward toward the Sun, from the moment of its discovery in late June 2025 until its perihelion passage on October 29th, the comet exhibited zero detectable non-gravitational acceleration. This was extraordinarily unusual. Most active comets show some level of NGA throughout their approach, as solar heating steadily increases and sublimation rates climb. But 3 I-Atlas moved like a dead rock, following a purely gravitational trajectory with mechanical precision. Then, at perihelion, everything changed. On October 29th, at the moment of closest approach to the Sun, when the object experienced its mysterious blue flash and dramatic brightening, something activated. Precise astrometric measurements from multiple observatories detected a sudden, powerful deviation from the predicted path. The comet had accelerated in a direction not entirely explained by solar radiation pressure or standard outgassing models. The numbers were staggering. Analysis revealed a 135-kilometer shift away from the Sun, combined with a 60-kilometer acceleration in the object's motion. Combined, these deviations totaled approximately 200 kilometers per day of non-gravitational acceleration. To put this in perspective, consider other famous comets with measured NGA. The interstellar comet 2I Borisov, the second confirmed visitor from beyond our solar system, exhibited non-gravitational acceleration of roughly 100 kilometers per day, about half of what 3I Atlas was now showing. But the comparison to solar system comets was even more dramatic. Comet Hale-Bopp, one of the largest and most active comets of the 20th century, visible to the naked eye for a record-breaking 18 months in the late 1990s, showed NGA measuring only 1% of what 3I Atlas was exhibiting. This made 3I Atlas the most extreme case of non-gravitational acceleration ever observed in any comet-like object in recorded history. The timing and magnitude of this acceleration raised profound questions. Why did it activate so suddenly at perihelion? Why was there no gradual build-up as solar heating increased during approach? What mechanism could produce such powerful thrust in such a short time? And most puzzling of all, why did the acceleration continue after perihelion, when the comet should have been moving away from the Sun and cooling down? Scientists proposed several natural explanations. The first and most conventional hypothesis suggested that the NGA resulted from asymmetric outgassing, triggered by the intense solar heating at perihelion. Perhaps the comet's rotation and shape created jets of sublimating ice that preferentially pointed in certain directions, producing a net thrust like a spacecraft's attitude control thrusters. This mechanism is well understood and explains the non-gravitational acceleration in many comets, but the numbers did not add up. To produce 200 kilometers per day of acceleration would require an extraordinary amount of outgassing, far more than what observations of the comet's brightness and coma suggested. The mass loss rates calculated from the dust and gas production did not match the thrust that would be needed to explain the observed course change. Something else had to be contributing to the acceleration. A second hypothesis proposed that 3I Atlas might have experienced a sublimation event involving super volatile ices, materials like carbon monoxide or nitrogen that vaporize at much lower temperatures than water ice. These materials could have remained frozen during the comet's approach, only to suddenly sublimate in a violent burst when the surface temperature reached a critical threshold at perihelion. This delayed outgassing behavior had been noted by scientists. The comet's activity seemed a bit delayed compared to typical solar system comets, with water vapor outgassing beginning much closer to the Sun than usual. However, spectroscopic observations from the Very Large Telescope, Gemini South and other major observatories had detected water, cyanide, nickel and various other molecular species in the coma, but no evidence of the massive amounts of carbon monoxide or nitrogen that would be required to explain the extreme NGA. The chemistry of 3I Atlas, while unusual in some respects, did not obviously point toward a reservoir of supervolatiles waiting to explode. Harvard astrophysicist Avi Loeb, known for his controversial theories about interstellar objects, proposed a more provocative explanation. Loeb had been studying 3I Atlas since its discovery, and the accumulating anomalies had convinced him that natural explanations were insufficient. The combination of delayed outgassing, extreme brightening, colour changes opposite to normal comet behaviour, and now the most powerful non-gravitational acceleration ever recorded, suggested something fundamentally different. In a paper published earlier in the year, Loeb raised the possibility that 3I Atlas might not be a natural object at all, but rather a technological artifact with active intelligence. If these lines are real, and not satellite streaks, they look like the trails of smaller objects that peeled away from 3I Atlas near perihelion, he noted, referring to unusual perpendicular features visible in deep space images. The problem, he emphasized, is that comets do not normally produce such sideways features. Their jets tend to point away from the sun because solar radiation pushes dust and gas in predictable directions. Loeb analogized the comet's presence to a blind date, explaining that you often assume that the dating partner would be very friendly. But you have to worry about serial killers as well. The hypothesis proposed is that 3I Atlas is a technological artifact with active intelligence, his paper stated. If so, two possibilities arise. Its intentions are either entirely benign or overtly malign. The non-gravitational acceleration fit this hypothesis in a troubling way. The sudden activation at perihelion could represent a gravitational assist maneuver, using the sun's gravity to adjust speed and trajectory, exactly as human spacecraft do when they perform slingshot maneuvers around planets. The course change would allow 3I Atlas to visit multiple destinations in the inner solar system. Loeb noted that the object's trajectory would take it unusually close to Jupiter, Venus, and Mars in the coming months. The scientific community remained deeply divided. Most astronomers continued to search for natural explanations, uncomfortable with invoking extraterrestrial technology when cometary physics, however poorly understood, might still provide answers. But the data kept accumulating, and each new observation seemed to deepen the mystery rather than resolve it. The Minor Planet Center announced a major global campaign, running from November 27, 2025 through January 27, 2026, to conduct intensive observations and refine measurements of 3I Atlas's exact position and motion. But the anomalies were not finished. As November progressed and high-resolution images arrived from multiple spacecraft, astronomers discovered that the non-gravitational acceleration was only part of a larger, more complex phenomenon. The comet had developed structures that should not exist: jets, plumes, and tails that violated the basic rules of how comets behave. What scientists saw next would push the mystery to its breaking point. When NASA released the latest images of 3I Atlas on November 19, 2025, the scientific community fell silent. The photographs, captured by a coordinated fleet of spacecraft including stereo, Mars orbiters, and ground-based telescopes, revealed structures that fundamentally challenged conventional cometary science. What observers saw was not a simple comet with the expected single dust tail and gas tail pointing away from the sun. Instead, 3I Atlas had developed at least 7 distinct jets, shooting in multiple different directions. Normal comets are relatively simple objects from a structural perspective. Solar radiation and the solar wind push material away from the nucleus, creating 2 characteristic tails. The dust tail, composed of heavier particles, curves gently along the comet's orbital path. The ion tail, made of ionized gas molecules, points directly away from the Sun, pushed by the solar wind like a flag in a breeze. This dual-tail structure has been observed in every comet humanity has ever studied in detail. It is one of the fundamental patterns of cometary behavior, as predictable as the sunrise. But 3I Atlas was rewriting the rules. The jets emanating from the object pointed in seemingly random directions. Some pointed away from the Sun, as expected, but others pointed toward the Sun, directly opposite to where radiation pressure should push them. Still others pointed sideways, perpendicular to both the Sun and the comet's direction of motion. These structures appeared distinct and well-defined, not diffuse clouds of gas and dust, but narrow, coherent streams of material. The orientation of these jets posed a serious problem for conventional explanations. When comets develop jets, they typically result from localized venting of sublimating ice from specific regions on the nucleus. As the comet rotates, these jets should sweep across space like lighthouse beams, creating smeared fan-shaped structures in long exposure images. Observations had determined that 3I Atlas rotates approximately every 16 hours. Over the course of the hours-long exposures needed to capture such a faint object, this rotation should have completely blurred any jets into broad halos, yet the jets remained sharp and distinct. Either the comet was not rotating as measurements suggested, or the jets were somehow maintaining their directionality despite the rotation, or something else entirely was happening that conventional comet physics could not explain. Harvard astronomer Avi Loeb noted that if these lines are real and not satellite streaks, they look like the trails of smaller objects that peeled away from 3I Atlas near perihelion. The problem is that comets do not normally produce such sideways features. Their jets tend to point away from the Sun because solar radiation pushes dust and gas in predictable directions. Then the jets began to merge. Within approximately 24 hours after perihelion, observers watched as the multiple distinct jets coalesced into a massive plume extending away from the Sun. This anti-solar plume grew rapidly, reaching a length of approximately 3 million kilometers, roughly 8 times the distance between Earth and the Moon. The scale was staggering. Material was being ejected from the nucleus at extraordinary rates, creating a structure visible across interplanetary distances. But the anti-solar plume was not the only tail structure. Simultaneously with its formation, a smaller feature appeared pointing in the opposite direction, toward the Sun. This sunward-pointing structure, often called an anti-tail, measured approximately 1 million kilometers in length. Anti-tails are not completely unknown in cometary science. They can form when Earth passes through the orbital plane of a comet, creating an optical illusion where dust particles lagging behind the nucleus appear to point forward. But 3I Atlas was nowhere near such a geometric configuration during its perihelion passage. Moreover, anti-tails, when they do appear, are typically faint, subtle features visible only in the most sensitive observations. The anti-tail of 3I Atlas was prominent and well-defined, captured by multiple independent observatories. Its presence so close to the Sun, exactly when radiation pressure should be most strongly pushing all material away from our star, violated basic physics. Something was driving material sunward against the overwhelming force of solar radiation. The Very Large Telescope in Chile captured some of the most detailed images of these structures throughout July and August 2025. The photographs showed a prominent sun-facing plume, visible in all images, pointing directly toward the star that should be repelling it. As August progressed, observers watched the comet begin developing its anti-solar tail simultaneously with maintaining its sunward plume. By August 27th, the Gemini South telescope revealed an anti-solar tail extending 30 arcseconds, corresponding to approximately 56,000 kilometers. The tail continued to grow. By September 15th, it had expanded to 50 arcseconds, or roughly 100,000 kilometers in physical length. The cyanide coma surrounding the nucleus had grown to 180,000 kilometers across, larger than the planet Jupiter, and showed a distinctly asymmetric structure elongated along the anti-solar direction. On the same date, observers documented a visible dust tail extending across the same scale. Michael Yeager, an experienced comet photographer, captured images on November 8, 2025, showing the fully developed tail system. By mid-November, the comet presented a complex morphology with multiple distinct features visible simultaneously. Ground-based observations from the Physical Research Laboratory in India, using their 1.2-meter telescope at Mount Abu, confirmed the presence of these structures and obtained spectroscopic data showing prominent emission features of CN, C2, and C3 molecules commonly seen in solar system comets. What made these observations particularly remarkable was what they implied about the nucleus itself. To produce such extensive outgassing, to create multiple jets pointing in contradictory directions, to generate plumes millions of kilometers long, and to do all of this while maintaining structural integrity required an object of extraordinary strength and mass. Normal comets are fragile. They fragment easily when subjected to thermal stress or tidal forces. The famous comet Shoemaker-Levy 9 broke into more than 20 pieces before colliding with Jupiter in 1994. Comet Ison disintegrated during its perihelion passage in 2013, torn apart by solar heating. Yet 3I Atlas, despite passing closer to the Sun than Ison, despite exhibiting 400 times brightening and extreme non-gravitational acceleration, despite producing millions of kilometers of tail material and multiple contradictory jets, remained completely intact. Observations from NASA's Stereo spacecraft, ESA's Mars Orbiter's Trace Gas Orbiter and Mars Express, NASA's Mars Reconnaissance Orbiter, and China's Tianwen-1 all confirmed that the nucleus had not fragmented. The object emerged from perihelion as a single cohesive body, its core unbroken. This structural resilience implied that 3I Atlas must be extraordinarily massive and dense compared to typical 3I Atlas comets. Most comets have densities around half that of water ice, making them fluffy piles of loosely bound material. But to survive the stresses that 3I Atlas had endured while producing such dramatic activity suggested a far more robust structure. Either the object was significantly larger than initial estimates of 5 to 10 kilometers diameter suggested, or it was made of unusually strong material, or both. Between October 30th and November 6th, 2025, NASA's Europa Clipper spacecraft was predicted to pass through the ion tail of 3I Atlas, potentially providing direct measurements of the tail's composition and magnetic structure. ESA's Hera spacecraft also potentially encountered the tail between October 25th and November 1st. ESA's JUICE spacecraft conducted observations between November 2nd and 25th. These encounters promised unprecedented data about the nature of an interstellar comet's outflow, but even as these observations continued and data accumulated, the fundamental questions remained unanswered. How could a comet produce jets pointing toward the Sun? What mechanism maintained their directionality despite the object's rotation? Why did the anti-tail appear at perihelion when it should have been physically impossible? And most troubling of all, what kind of object possessed the strength to hold itself together while ejecting such enormous quantities of material in multiple directions simultaneously? The answers, if they existed, would have to wait for the next critical observation window. December 19th, 2025, the date when 3I Atlas would make its closest approach to Earth. As November 2025 drew to a close, astronomers around the world found themselves confronting a profound realization about 3I Atlas. This was not just another comet, not just another interstellar visitor making a brief appearance before disappearing forever into the cosmic night. The accumulating data pointed towards something far more remarkable and far more rare than anyone had initially suspected. The size estimates kept growing. Initial observations from the Vera C. Rubin Observatory during its science validation phase in late June and early July 2025 had provided constraints on the nucleus diameter, suggesting the comet was relatively small. The Hubble Space Telescope refined these estimates on the 21st of July 2025, with high-resolution images that constrained the nucleus diameter to below 5.6 kilometers. This would make it a modestly sized comet, comparable to many others in our solar system. But as observations continued and the comet's behavior became increasingly anomalous, scientists began to question these early estimates. The structural integrity that 3I Atlas displayed, surviving perihelion passage without fragmentation despite extreme thermal stress, suggested a much more massive object. The enormous tail structures extending millions of kilometers, the multiple jets pointing in contradictory directions, the extreme non-gravitational acceleration, all of these phenomena pointed toward a nucleus substantially larger and more robust than 5 kilometers across. Conservative estimates now place the object at approximately 5 kilometers in diameter, but other scientists, analyzing the mass loss rates, the brightness variations, and the gravitational effects on nearby spacecraft, argued for a much larger size. Some estimates suggested the nucleus might be closer to 10 kilometers wide. This would make 3I Atlas approximately 20 times larger than Oumuamua, the first confirmed interstellar visitor discovered in 2017. It would also be roughly 10 times larger than 2I Borisov, the second interstellar object and the first confirmed interstellar comet. A massive interstellar object, 10 kilometers across, that has survived billions of years traveling through the galaxy, represents something extraordinarily rare. Most objects of this size would have been captured into orbit around stars long ago, ground down by countless collisions with interstellar dust, or torn apart by tidal forces during close encounters with stellar systems. For such an object to remain intact for the age of the universe, to cross the vast distances between stars without being destroyed or significantly eroded, requires a combination of circumstances so unlikely that it borders on impossible. The probability calculations painted a sobering picture. In any given year, perhaps one or two interstellar objects the size of 3I Atlas pass through the inner solar system within a few astronomical units of the Sun. Most go completely undetected, too faint or too distant to be spotted by even our best telescopes. Of those rare visitors that do pass close enough to observe, the overwhelming majority arrive during times when our detection capabilities are limited, when key telescopes are offline, when the geometry is unfavorable, or when the Sun is in solar minimum and the visitor exhibits minimal activity. For 3I Atlas to arrive precisely during solar maximum, when the Sun's fury would trigger maximum cometary activity, making it dramatically easier to detect and study, represented a stroke of extraordinary luck. For it to pass this close to both the Sun and Mars, bringing it within range of multiple spacecraft simultaneously, added another layer of improbability. And for this to happen during an era when humanity possessed the technological capability to observe it with sophisticated space-based and ground-based instruments, when international cooperation enabled coordinated observations across multiple agencies and nations stretched the bounds of coincidence. Scientists estimated the odds of such a perfect alignment of circumstances at roughly 1 in a million, humanity had won a cosmic lottery, granted a front-row seat to observe an interstellar visitor under optimal conditions, and astronomers were determined not to waste this opportunity. NASA had mobilized an unprecedented observational campaign. The Stereo spacecraft continued tracking 3I Atlas as it moved away from the Sun, documenting changes in its tail structures and monitoring for any new anomalies. Multiple Mars orbiters, including ESA's Trace Gas Orbiter and Mars Express, NASA's Mars Reconnaissance Orbiter, and China's Tianwen-1, had all captured images during the comet's close approach to Mars on October 3rd. The data was still being analysed, but preliminary results showed the comet had passed within proximity of the red planet without any apparent gravitational deflection, another testament to its unusual properties. The European Space Agency's JUICE spacecraft conducted intensive observations between November 2nd and 25th, 2025. ESA's Hera mission had potentially encountered the comet's ion tail between October 25th and November 1st, providing valuable data about the composition and structure of material being shed by the nucleus. NASA's Europa Clipper was predicted to pass through the ion tail between October 30th and November 6th, its sensitive instruments measuring magnetic field distortions and plasma characteristics. Ground-based observatories joined the campaign. The Physical Research Laboratory in India used their 1.2-meter telescope at Mount Abu to capture both images and spectra of the comet in mid-November. The spectroscopic observations revealed prominent emission features of CN, C2, and C3 molecules, bands commonly seen in solar system comets, confirming that at least some of 3I Atlas chemistry matched familiar patterns. The Very Large Telescope in Chile, the Gemini South Telescope, and dozens of other facilities contributed observations throughout the autumn months. Amateur astronomers played a crucial role as well. Michael Yeager, an experienced comet photographer, captured detailed images on November 8th, showing the fully developed tail system. Backyard telescopes with apertures as small as 3 to 4.5 inches successfully imaged the comet, though it remained far too faint for visual observation even through large amateur instruments. The global astronomy community, professional and amateur alike, united in studying this remarkable visitor. But all of this was merely preparation for the main event. The date circled on every astronomer's calendar was December 19th, 2025. On that day, 3I Atlas would reach its closest approach to Earth, passing at a distance of approximately 1.8 astronomical units, roughly 269 million kilometers. While still an enormous distance by terrestrial standards, far beyond the orbit of Mars, this would bring the comet close enough for ground-based telescopes to obtain their best views. Every major telescope on Earth and in space would be pointed at 3I Atlas during this critical window. The James Webb Space Telescope, with its unprecedented infrared sensitivity, would search for exotic molecular signatures in the coma. The Hubble Space Telescope would capture the highest resolution images of the nucleus ever obtained. Radio telescopes would listen for any electromagnetic emissions. Ground-based observatories would conduct intensive spectroscopic monitoring, tracking changes in composition minute by minute. Scientists expected new surprises because 3I Atlas had consistently defied predictions at every stage of its passage through the solar system. The object had revealed layer after layer of anomalous behavior, each observation raising more questions than it answered. The delayed outgassing that only began far closer to the Sun than normal, the 400 times brightening that exceeded every model, the color changes from red to green to blue, opposite to conventional comet physics, the sudden activation of extreme non-gravitational acceleration at perihelion, the multiple jets pointing in impossible directions. the sunward anti-tail that should not exist, the structural integrity that allowed the object to survive conditions that should have destroyed it. Harvard astrophysicist Avi Loeb noted that we are observing something completely unprecedented in the history of astronomy. Whether 3I Atlas is an unusually robust comet with exotic composition, or represents something fundamentally different from any natural object we have encountered, remains an open question, but the data we collect in December may finally provide answers. The Minor Planets Center announced a major global observation campaign running from November 27, 2025 through January 27, 2026, coordinating efforts across dozens of institutions worldwide. Every data point mattered. Every spectrum, every image, every measurement contributed to unraveling the mystery of this extraordinary visitor. As November turned December, 3I Atlas continued its outward journey, moving away from the Sun but approaching Earth. Its tail stretched across the sky, visible now to moderately sized telescopes in the pre-dawn darkness. Its coma glowed faintly, still active despite increasing distance from solar heating, and deep within that haze of dust and gas, the nucleus rotated silently, keeping its secrets, waiting for December 19th when humanity would get its closest, clearest view of an object that had travelled for billions of years across unimaginable distances to visit our small corner of the galaxy at precisely the moment when we could witness its passage and wonder at its mysteries.